In part 4, we're going to be looking at finding the inverse of a function. So let's say that we have a particular function that we're working with, and we would like to have the inverse of that function as well. And there are many applications that are interested in having the inverse to go with it. One in particular is the field of encryption. If you are buying things online using credit card information, your laptop or computer or your cell phone, whatever it is, will take your credit card information and it will put it through a function known as the encryption algorithm or the encryption function. And then once that information is encrypted, it's very difficult to read by someone who might be trying to steal your credit card information. But once that information gets over to the service provider, such as Amazon, Google, maybe you're doing some kind of online banking with Wells Fargo, Bank of America, they have to have some way of being able to undo the encryption. This is called decryption. Well, that would be analogous to the inverse function of whatever the encryption algorithm was. So having a function and then having its inverse as a pair can be really, really powerful in data security, and that is always a hot topic in today's society. People get their identity stolen all the time, or credit card information stolen all the time. So let's talk about the procedure for how to be able to find the inverse of a function. So the first thing I do is I write y equals f of x. So I'll take whatever my function equation is and I'll write it as y instead of f of x. So this is just removing the function notation. That's what step 1 is. Step number 2, though, is really important. It says check to see that an inverse function is possible. Now we know that an inverse function is possible if your function is one-to-one. We've had those conversations back when we talked about the definition for the inverse. You have to start with a one-to-one function in order for this process to even work. So the best way to do this is to just graph your function and then apply the horizontal line test. That's what HLT means, horizontal line test. So I think that's where we're going to start. Let's go ahead and look at example 17.5, and we can always come back and look at some of these steps a little more closely. 17.5, it says find an equation for f inverse of x, also known as the inverse function. We know that already. Then plot f and f inverse on the same coordinate grid. And for part A, we have f with the domain of all real numbers, given by f of x equals 2x plus 3. So I'm going to take f of x and think of it as y equals 2x plus 3. Hopefully you're recognizing this as a linear function, and a linear function should have no problem passing the horizontal line test, but it's good to go ahead and graph it and then see that for yourself. Y-intercept would be 3, slope is 2 over 1, so we'll go up 2 over 1, down to left 1, down to left 1, and without a ruler, try to put as many points on here as you can. And that's close enough. That is going to be the graph for f. Certainly that would pass the horizontal line test, no problem. Now let's proceed to step number 3. Step number 3 says to switch the role of x and y. Now I'm a big proponent of actually spelling out what you're going to be doing. Don't surprise me with switching the x and y. Tell me that you're going to do it. So we're going to say switch x and y. And then when that happens, my equation now says x equals 2y plus 3. So this is an example of an implicit inverse. So this is technically the inverse, but it is not in the format that we want. This is a implicit inverse, and we need to have an explicit inverse where it's y equals and not x equals. So creating the inverse automatically switches the x and y. It automatically makes this say x equals. So then it's up to us to rearrange the terms to get it back to being y equals. So we're going to subtract 3 from both sides to get x minus 3 is equal to 2y. And then I'm going to divide both sides by 2, and that's going to get x minus 3 over 2, all equal to y. And then I'm going to take it a step further and go ahead and divide x and 3 by 2. That's going to result in 1/2 x minus 3/2 is equal to y. Now both of these lines are really an acceptable stopping point. These are both the explicit inverse. And the explicit inverse is what we're looking for in step number 4, where it says to solve for y. So I didn't mention that, I just kind of rolled into that step, but that's what we were doing just now with step number 4, solving for y. And then on step number 5, it says to write y is equal to the f inverse of x. So this means that I'm just going to rewrite this bottom line as f inverse of x is equal to 1/2 x minus 3/2. And this gives me the equation for the inverse. So I want to graph that at the same time as f. That's going to be a y-intercept of negative 1.5. The slope is up 1 over 2. And I'll do that several times. I'll also go back and go down 1, left 2 several times until I can get enough points to draw a straight line, semi-straight line. It's always tough to do this on the digital pad here. Yeah, it's close enough. There's f inverse. And the observation that we will make here is the same one we did back on example 17.2. Anytime you plot a function and its inverse at the same time, you should be able to graph the line y equals x and observe that the line y equals x is a line of reflection for these two functions. And the one place that these functions intersect is right there on top of the line of reflection, y equals x. So this is the procedure for finding the inverse, and then we went ahead and also just plotted it so that way we could see the connection between the two graphs there with the line y equals x.